All right. We are wrapping up Unit 8 today, which is using the frequency response to design systems. What we did last time was a 1 hour long demo problem. Let me bring that up on the PowerPoint now. It was a 1 hour long demonstration or example in which we took a plant that has a single integrator and a couple of real poles. And we saw that under some proportional controls it was stable, and under some proportional controls it was not stable. The argument for not using proportional control here is that it would cause the overall system, the closed-loop system, to become sluggish and have a small bandwidth and have a small rise time. Or sorry, a long rise time, so a poor performance. The alternative that I proposed was what's called a lead compensator, which the idea, the conceit of which is if we could only boost the phase plot in a small range of frequencies without really touching the magnitude plot, then we could buy ourselves some gain in phase margin and stabilize the system without resorting to shrinking the bandwidth unnecessarily. So that's what we have on the screen here. If you found this difficult to follow, I don't blame you. There was a lot of sketching involved. So what I'd like to do now is actually bring you over to Matlab and show you maybe something a bit more analytical. Quick check. Can you see SISOtool? Anyone give me a thumbs up?
Yep.
Okay, so what I've got here is the P block, so 3162. There it is, 3162 divided by S plus 10 quantity squared. And this is the plant. And by default, the SISOtool controller block is value of 1. And so we can see that this also answers our question that under proportional control, when that constant is set to 1, there are closed loop poles in the right half plane. If we kind of break our gaze away from the root locus and look over here at the Bode plots, and loop transfer C is MATLAB speak for the open loop transfer function. We can see that the gain margin is reported at -4 dBs and the phase margin at -12 degrees. Okay, so all of those things point to an unstable system. And just like we saw before, if we reduce the gain by about 4 dBs, we can stabilize this system, right? We now have a positive gain margin. We now have a positive phase margin, and that all works. However, look what we have to do, or look at the trade-off here. If I reduce the gain further, so first off, I want you to see that in the step response here, the overshoot is, by any stretch of the imagination, unacceptable. So if I reduce the gain to make the overshoot acceptable, I make the rise time quite long. Okay, so that's the trade-off that we were talking about. It's super duper stable, 20 dBs of gain margin, 66 degrees of phase margin. This is as stable as you could want a system to be. But we pay for it with a sluggish transient response. Okay, so that was the rationale. If instead of a proportional controller, we add a lead compensator, so we could either use the Matlab lead, or what I'm used to doing is I'm adding a pole and a 0 individually. So the proposed topology was a pole at -100. And a 0 at -10. And so by adding 1 pole and 1 0, we're not actually changing the asymptotes. They will still go into the right half plane. But what we can do now is, and by doing this, and with the current gain, 0.68, we have a very stable system. But now we can go ahead and increase the open loop gain Usually that works. I clicked on the magnitude response and I'm dragging it up to simulate increasing the gain. There we go. Okay. So now what we can do is we can play around with 3 degrees of freedom, just like in experiment 4. We can play around with the 0 location, the pole location, and the gain. So I think in lecture, we set the gain to be 1. So that shows up here as 10, s plus 10 over s plus 100. And here we have a bit of a compromise, right? We've got 50% overshoot, but we've got a nice snappy rise time. So I'm not claiming this is the best design, but I am claiming that we are seeing a better compromise between transient performance and stability using the lead compensator. Okay. So the other thing we can do is I think we can actually look at the Bode plot of the compensator block itself. So I'm going to go to New Plot. I'm going to create a new Bode plot. And I want to see the frequency response of this block itself, just the C block. So because it's not in the listed list of signals here, I'm going to create a new input-output response where the input is the E signal, the output is the U sub C signal, and I think that should be good. That is not good. My bad. Try it again. Let's do new response from E to UC, and we're going to open the loop at UC. Okay, that should do it, I hope. There it is. Okay, so this is what I was trying to draw in the second to last slide of Monday's lecture. And this is the phase boost that we see from the lead compensator. So let me try and get all of these 4 windows simultaneously. There we go. So here I can demonstrate that if I move the compensator pole away from the 0, then the phase boost increases. Right, so the height of this hump gets higher, but we pay for that with a larger high-frequency magnitude gain. If I do the opposite, if I move the compensator pole closer to the 0, then the opposite happens. We get less phase boost, but we have only a 15 dB payment for that at high frequencies. And the same would happen if you moved the 0 as well. We can move the location of the maximum phase boost if we move the pole and the 0 the same distance. So if I wanted to put the boost at a higher frequency, I would move the pole up, and then I would come back here and I would grab the 0 and I would move the 0 up. So the idea here is that the location, the place that you are going to amplify the phase the most is also free for you to choose by moving the pole and the 0 to different frequencies. And lastly, I think, let's move this back down a little bit. Okay, so we have 10 dBs of gain margin and 23 degrees of phase margin, which means that for this design, we can actually bite into that gain margin a little bit and move the magnitude curve up. And then we can iterate this process and kind of diminish, diminish the phase boost. And perhaps because of the overshoot, maybe we want to actually drop the gain a little bit from there. That's pretty good. That's what, 25% overshoot and 0.2 second rise time. That's significantly better than what we were able to accomplish with simply proportional control. Okay, we've got plenty of gain margin, we've got plenty of phase margin. This is a pretty well stabilized and pretty decent performing system. So any questions on this? This was essentially exactly what I was doing by hand, but using SISOtool. Okay, let's switch back to the PowerPoint from yesterday because I got a little carried away. So one more thing that I want to talk about is another perspective on a concept that we've already learned, and that is the dominant pole approximation. I told you that you're not always going to get root locus diagrams when you buy equipment. You're more likely to get Bode plots or frequency responses. How will you be able to tell, does the system act like a first order, a second order, a third order, et cetera? How could you ever know that? So let's start with the easy case. Let's start with the case where we've got an obviously slow pole and an obviously fast pole. Call this pole 1, call this pole 2. And if you like, let's make it explicit. Let's say that P2 is 10x P1. So the magnitude plot, if you look at it, it's going to be whatever it is at low frequencies. And then if this is pole 1, we're going to drop by 20 dBs per decade until we get to pole 2 frequency, at which point we're going to drop by 40. So here's 20, here's 40. So, and let's say that these are closed loop poles. And this is then the DC gain of the system. So I want you to see that if we take the notion of bandwidth that we learned earlier, then this is the bandwidth of this closed loop system. And so what we can see is that we can kind of meld the concept of system bandwidth with the idea of dominant poles. And we see that in the absence of any zeros, so kind of in the easiest case, the bandwidth, anything that lies outside the bandwidth can largely be ignored, right? That's kind of what we're saying here, is that this is a psi of 10. And so we would say that this pole dominates. And another way to see that is that that pole is the corner of the system's bandwidth. That this pole kind of lies in the stop band of the system. Okay, so again, this pole is the one that you would pay attention to when analyzing the system for transient performance. Now, the psi of 10 is up for negotiation, particularly if we move pole 2 maybe to back here. It's still going to be dominated, perhaps less so, but certainly if we move pole 2 in this direction, then this kink here occurs even lower. Where would it be? It would be here. And so the fact that you have a kink at 40 dBs below DC gain suggests that its importance is not terribly high. Questions on this? Because I'm gonna consider the slightly more complicated case next. Okay, so let's reset. Oops. Okay, so let's talk about what happens when we've got a pair of, say, dominant complex poles and a dominated third pole, real pole. So let's call this sigma, and let's call this P. Then what are we looking at here? Well, we've again got the DC gain, whatever that happens to be. And once we get to omega n, then we are going to see something like the peak of the resonant frequency for these pair of poles. So let's call this omega n. And then depending on the zeta, we are going to get either a peak or a sag, but that action is going to happen around about omega n. And if P, say, is, well, if we want to make it 10x, then we would have an extra pole. So here's omega n, and here's our 2040 dB per decade asymptote. Nope, that's not how dBs per decade works. That's what I'm looking for. There we go. So the question now is, everything we've learned about dominant pole has been real part of the pole versus real part of the other pole. So how does sigma, the real part of the complex poles, how does that relate to omega n? Well, it has to be less than, right? It's the leg of a triangle, and omega n is the hypotenuse of a triangle. So this is going to be less than or equal to omega n. Which means that if P is something like 10 omega n, that means that P is at least 10 sigma. And so if we use the omega n as our metric instead of the real part, then we are guaranteed a better psi ratio or a larger psi ratio. So that's what I'm looking at here, is if we have this guy coming down here, and then if we put P at 1 decade above omega n, then at this point, now we're looking at 60 dBs per decade. So we'd have just that. But my point here is that this kink is once again buried in the stop band. Uh-oh. Oh, yes. There we go. Okay. This is getting sloppier every time I do it. The extra kink, so if this is omega n and this is P, this is lost in the stop band. Now, the closer we make P to omega n, then all of a sudden that kink might occur here. And then it becomes a question of, is it ignorable or not? Certainly the closer P gets to omega n, the less ignorable that pole is. Okay, so basically what I wanted to call your attention to here is that the dominant pole measurement psi is really helpful, or it can be viewed in terms of the system bandwidth. And really what you're saying is, when you say the system has 95 kilohertz of bandwidth, is that your slowest pole corresponds to 95 kilohertz. That's essentially what you're saying. And that your system might have more poles, but they are going to be at higher frequencies than 95 kilohertz. So therefore, there is one argument to be made that they are negligible. Okay. Now that is taking a lot for granted. It's assuming that your dominant pole is real. So if your dominant pole is not real, I guess it's a little bit too much to say. If I say the system has bandwidth of 95 kilohertz, then I think that tells me that there are no poles slower than 95 kilohertz. It doesn't tell me exactly what's going on at 95 kilohertz. I could have a real pole. I could have a pair of complex conjugate poles in that region. But the idea is that within a couple of kilohertz of 95, that's where the first dynamics of the system come into play. Okay, I think that's an accurate story. Questions on that? So this slide is simply a summary of what we've learned in units 7 and 8. And it's trying to clarify which transfer function do you use to measure which thing. What we spent the most time on in this unit is right here, is talking about gain and phase margins, and those are definitely, you need to read them from the open loop Bode plot, even though they tell you about closed loop stability. So that's the kind of key there. You saw in the homework that you can determine the type number from, in a unity feedback system, from the low frequency slope of the open loop Bode plot. In particular, if you've got an open loop Bode plot whose low frequency slope is 0 or close to 0, then you know that it's a type 0 system. If, on the other hand, your open loop Bode plot goes like this, then depending on the slope here, it's going to be a type N system. If it's 20 dBs down, then it's a type 1 system. If it's 40 dBs down, then it's a type 2 system, et cetera, et cetera. Now, most of the time we talk about these magnitude plots because magnitude plots are actually the easier ones to measure. You don't need super sensitive equipment to measure magnitude plots. You don't need as sensitive equipment to measure magnitude plots as you do to measure accurate phase plots. But I also want to point out that if we have a phase plot and we're confident that it's accurate, it can actually be a way better way to tell what your system type number is. So in particular, open loop Bode phase, if your low frequency phase is 0, then you can't have any integrators because every integrator has a constant phase of -90. So this would be a type 0 system. And I like the phase plots for this because differentiating between a phase of 0 and a phase of 90 or a phase of -90 tends to be easier if you've got accurate phase data, which again is harder to get in the first place. This is an easier graph to read than you saw in the homework where, what is that? Is that flat? Is that kind of just an intermediate dip? So the magnitude plot is easier to obtain, but sometimes more difficult to interpret. Okay? So a lot of what sets a nice lab apart from a shoddy lab is that the ability to make detailed high frequency phase measurements. And if you think about why that's difficult, think about the timing required in these digital instruments to measure phase differences at kilohertz, at megahertz, at gigahertz, right? A couple of degrees of phase at a gigahertz is fractions of a nanosecond. So if you're measuring a phase as a phase difference as the difference in zero crossings, which is typically how these phase plots are, these phase measurements are made. This difference in absolute time units gets teeny, teeny, tiny as the frequency increases. Okay, so this is the reason why you would pay $1,000 for a spectrum analyzer, and you might pay $10,000 for a full-blown signal analyzer that has high-frequency phase measurement capabilities, because it's just harder to build electronics to measure those kinds of small time deltas. All right, that is the conclusion of this note set. I did cook up a new note set on sensitivity, and I've posted that to PolyLearn just before class started. So I will pull that up, but I'm happy to answer any questions on this note set if you have them. Okay, so system sensitivity, and like I said, this is the topic of system sensitivity gets bounced around, at least in the way that I teach this class. I used to include it earlier, like in the steady state unit, but it didn't really fit well there. I used to include it in the Unit 7, where we're learning about Bode plots more accurately. And this quarter, I figured it was the least valuable fruit to cut if we didn't get time for it, which is why it's kind of tacked on here at the end. But I think it's an interesting topic. It broadly falls under the category of why are closed loop systems better than open loop systems? And that is one of the themes. I haven't had a lot of time to kind of review the themes of this course, but now that we're winding down, might as well start. One of the themes of this course was closed loop topologies are often better than open loop topologies. And you ask why? Well, we can move the closed loop poles to be in faster locations than if we use feedback than if we just used open loop topology. We can stabilize otherwise unstable open loop systems if we use closed loop control. And we can reduce sensitivity if we use closed loop control rather than open loop control. So let me drill into that last statement. Why would we want to reduce sensitivity? And again, this is system sensitivity. In the face-to-face version of this class, there's the joke of like, as humans, we want to be sensitive to each other, but as systems, we actually want to reduce our sensitivity. So the idea is that no one ever really knows the exact transfer function that represents the system. There is always some uncertainty in, say, the pole locations or the parameter values or the frequency response. There's going to be some uncertainty. You could model something from very first principles, and there would still be uncertainty in the measurements you made. So was that motor spinning at 1,000 RPMs or at 1,005 RPMs, right? We've talked about this a little bit with kind of the pole zero cancellation in the right half plane, is that you're never quite sure that a pole is where you think it is. You're never quite sure that a zero is where you think it is. The more expensive, the more money you pay for the better components, the more sure you are of what those component values are, but you're never, ever absolutely sure. And so this concept of embracing uncertainty, okay, we're getting meta here. The concept of embracing uncertainty is something that good engineers do, and bad engineers kind of sweep it under the rug. You can design systems well, even if you are uncertain of their exact parameters. Okay, I don't think that's too broad of a statement. So I've got the MCSL from the lab, this block diagram up on the screen now. And I just bring this up because in our very first experiment, I asked you to derive the gains of these blocks, as well as the gear ratio here and the time constant here. And in the discussion of that experiment, I asked you to try and quantify your uncertainty in these parameters. Now, for example, the Ka is measured in what, volts per volt. So volts in, volts out. And we got something like roughly a straight line. And the idea was that you picked your favorite computer program to give you a best fit line. But these data points, if you were to be honest with yourself, they have error bars, both in the vertical and in the horizontal. Right, because we used a finite precision multimeter to measure the input voltage as well as the output voltage. And so you could continue this, blah, 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 blah. And at the end of the day, I hope you can see that if these error bars were kind of interpreted as a range of uncertainty. So I think the data point's in the center, but truly the data point could be anywhere in there. A more sophisticated model would actually associate probabilities with where the data point ought to be. But for now, let's just say the data point could be inside the bars and it can't be outside the bars. Maybe uniformly, however you want to talk about that. But I hope you can see that there are now multiple quote unquote best fit lines that could lie in all of these error bar ranges. Yeah, and then the nominal, Ka nominal, is different than Ka minimum and Ka maximum. Now, it usually works out that the nominal value is kind of in the middle between the minimum and the maximum. That doesn't have to be. But what you can do is you can talk about the uncertainty in Ka as maybe, I don't know, there are lots of ways to quantify it. You could talk about half the distance between the min and the max. So delta Ka might be something like Ka max minus Ka min divided by 2, something like that. Or you could try and do the average. You could add these and then subtract off the Ka nominal. Right, there are lots of ways to find that, but the idea here is that this represents the error in Ka. And I'm going to refer to this as the absolute uncertainty. Absolute uncertainty, which is kind of a strange phrase when you think about it. How could something be absolutely uncertain? But absolute in terms of absolute versus relative. So the error in Ka, or this absolute uncertainty, isn't typically how we talk about uncertainty. It's more common to talk about uncertainty in terms of its relative uncertainty. So that would be delta Ka over Ka nominal. And usually we just leave off the nominal, it's just Ka. So this is one way to quantify relative uncertainty. And the nice thing about relative uncertainty is that it's unitless, or its units are percent, right? Because if delta Ka is measured in the same units as Ka, then this fraction has no units. So this is what I'm going to talk about when I talk about parameter uncertainty, this relative uncertainty in a given parameter. Now, I just picked Ka because it was kind of the first thing in the diagram here. There will also be uncertainty in Km, uncertainty in N, and the list goes on. Everything that we measured has measurement uncertainty, and if we did manipulations to those measurements, calculations, then we propagate that uncertainty down the line. Okay, so the Km that we have been using, the Ka that we have been using, ought to be called the nominal values of those things. They're shrouded in a cloud of uncertainty. We think they're in the center, but they could be anywhere in there. Now, that is talking about uncertainty. Sensitivity is how much does the uncertainty in a parameter affect uncertainty in the overall system? Okay, so think about that. I'm defining sensitivity, a system's sensitivity to uncertainty in a parameter, and I'm going to abbreviate that to be just sensitivity. A system's sensitivity acts like a gain, and that's my favorite way of thinking about this, is that the sensitivity of T to K acts like a multiplier on the relative uncertainty in K to give us the relative uncertainty in the system T. So I'm saying T is the transfer function, K is the parameter. K lives inside of T somehow. We don't exactly know how. But just in general, a system can have multiple parameters. Therefore, there will be multiple sensitivities. So this is how, this is one of my least favorite notations in this entire class is this capital S stands for sensitivity. The superscript stands for the system that we're checking the sensitivity to. The subscript represents the parameter we're checking the sensitivity of. And if you wanted to be super complete, because this is a function of S, the Laplace S, this also ought to be a function of S, the Laplace S, okay? So this is my favorite way of thinking about how sensitivity should be interpreted. If, okay, let me put this to you. If all other things were equal, would you like the sensitivity of T to K to be a large number or a small number?
Small number?
The smaller it is, the less uncertainty here gets mapped to there. Exactly right. So as engineers, and think about it this way, I think this is a very natural way to think about it. Resistors come with different tolerances, right? You can buy 10% resistors, you can buy 5% resistors, you can buy 1% resistors. That percentage, that tolerance, is exactly what I'm talking about in relative uncertainty. Now, wouldn't it be nice if you designed the system such that a 10% uncertainty in resistance 1 resulted in a 1% uncertainty in the overall transfer function, right? That would be a decrease by a factor of 10. That would mean you could buy the cheap resistors and still have great performance. Okay, so that's the idea here. If I want this to be, you want this to be small. That way you can buy cheaper things, you can be more uncertain in your parameters and not pay for it with uncertainty in the transfer function. Now what it means to have an uncertainty in the transfer function, that is actually a little bit murky in itself. But I think everyone would be okay with, if I'm uncertain in a transfer function, then I would be uncertain in a step response, or I would be uncertain in a Bode plot. Exactly how that maps is a little bit nebulous, but certainly if I decrease uncertainty in a transfer function, I will increase my certainty in where the output due to any given input the system will lie. Okay. So this slide is meant to introduce you to this concept of sensitivity. But this top line is not actually how we commonly compute sensitivity. What we typically do is we divide both sides by delta K on K. And then you can fix this up by moving the fractions around. And then the way that we get this absolute error down to become these partial derivatives is we just talk about the marginal error. So this is kind of like an in the limit situation. In the limit as error, as delta error becomes infinitesimal. So the idea is you can get from this line to that line if you consider marginal changes in uncertainty. And that's what these partial derivative operators are supposed to represent. So in the limit, and this is how we typically compute sensitivity, is we take the partial derivative of the transfer function with respect to the parameter that you want, and then we multiply that by the parameter divided by the transfer function. Okay. So this is my favorite way of thinking about it. This is my favorite way of computing it. They are equivalent, provided that you take everything in the limit. All right. Questions on this slide?
In this example, we are going to answer the question, which of these two systems is less sensitive to the pole location P? The options are the open loop system, which is the first order system G, or the closed loop system around G. So this will give us some opportunity to calculate some sensitivities. So again, the sensitivity of G to P as a function of S is the partial derivative of the transfer function with respect to the parameter times the ratio of the parameter to the transfer function. So let's work on this partial derivative a little bit. I can write this g function equivalently if I multiply top and bottom by p as p times k over s plus p, and then I can use the quotient rule there. So if I want to take the derivative of g with respect to p, I need to do low d high, so s plus p times the derivative of the top with respect to p minus top times the derivative of the bottom. With respect to p, it's just 1. And then divide by the denominator squared. Okay, so that is all the derivative, and then we multiply that by this ratio p over g of s. But g of s is more helpfully written as p times k over s plus p. All right, and this is the big fraction bar. Okay, so we're going to get some cancellation. So this p and that p will cancel. Here is a plus p times k, here is a minus p times k. And once that happens, then this k will cancel that k. And one of these will cancel one of these. So at the end of the day, the sensitivity of the open loop transfer function with respect to the pole location p appears to be s over s plus p. Okay, so whether that's good or bad, it's kind of hard to say at this point. It is a function of s, so it is difficult to say, is this a big number or a small number? Because, of course, the magnitude will depend on the argument s. So this is what I was getting at, is that the value of a sensitivity is lower in isolation. They are more valuable when you can compare one sensitivity to another. So that's why this is a two-part example. Let's work out the closed loop transfer function over here. Which is, of course, g over 1 plus g. And if I write g in this way, then I think we get p times k over s plus p times k. And if you like, we can factor the p in the bottom, so we get s plus p times 1 plus k. There we go. Okay, so then the sensitivity of the t transfer function, the closed loop transfer function with respect to p as a function of s, is going to be the derivative of t with respect to p times this normalization, p over t. All right, so this partial derivative, again, we can use the quotient rule. So we get s plus p times 1 plus k times the derivative of the top with respect to p minus the top times the derivative of the bottom with respect to p, which I think ends up being 1 plus k. Divide that by the denominator squared. And then, again, that's the partial derivative term. And then we're going to multiply that by p over the closed loop transfer function. All right, again, lots of cancellations will occur. So p and p. Here is a minus p times k times 1 plus k, and here is a positive p times 1 plus k times k. So those two will cancel. And one of those will cancel with one of those. So let's see what that gets us. I'm left with an s times k over this k. Okay, so yeah, this k and this k will then cancel. So we can lose that k. And we get the denominator s plus p times 1 plus k. All right. So at this point, you could probably have a good idea of which of these two functions is larger or smaller, because their format is largely the same, right? They both have an s in the numerator and nothing else, and they both have an s plus a constant on the bottom, and the constant in the closed loop case is larger than in the open loop case if we let k be positive. So there is some indication there that the closed loop sensitivity will be lower than the open loop sensitivity, but I want to give you a more general way to show this in case the two functions are not directly applicable or directly comparable. So the way to go about this is, instead of looking at these as a function of s, let's look at their magnitudes as a function of omega, right? So this would be, as they appear, they are functions of the Laplace s, but what we do if we let s be j omega is we're saying how sensitive are these systems when operated at frequencies omega. So that's the slightly less broad question, but still a valuable one to ask. And instead of the complex number output, let's talk about the magnitudes. So I'm looking at the sensitivity of the system G with respect to P as a function of omega, and we're going to do these in decibels, and that's why I've left this to the frequency response chapter. But we get j omega over j omega plus P over here. And if you do the same operation over here, we're going to get the magnitude of the top and j omega plus P times 1 plus K. Neither of these are in leading ones form, so perhaps we ought to do some work and manipulate them into that form. So I think we'll get 1 over P j omega over P plus 1. I think that's how that should work. And in the same story here, we're going to factor out the P times 1 plus K. So we get 1 over P times 1 plus K times j omega over that quantity, P times 1 plus K, plus 1. So there's leading ones form in both sensitivities. All right, so now let's do some work and plot these magnitude responses on graph paper. Okay, so this was the open loop sensitivity, and this was the closed loop sensitivity. These are going to be tough to draw if we don't have some nominal values for P and K. So let's let P be 100 radians per second, and we'll let K be 1. And then we can see how this would change if those values change. So let's draw the constituent pieces. So here let's put 0 dBs right there, and we'll say this is 100 radians per second, making this 1 radian per second. And so the constituents of the open loop sensitivity are the differentiator. So we've got a 20 dB per decade slope from the differentiator in the open loop. We have a 1 over 100, so a minus 40 dB contribution from the constant. And we've got a pole that kinks at 100 radians per second. So we get this business. Okay, so these are the three constituents. We have the differentiator, we have the constant, and we have the real pole. Those are the three components that I've drawn there. And so let's overlay those. So the constant is going to drag the differentiator down. So we get behavior like this until we get up to this pole where we have a plus 20 and a minus 20. So after this point, sensitivity is flat. Okay, so that is the sensitivity of G with respect to P in magnitude in dBs. All right, so let's clean up the drawing a bit here. I'm actually going to leave the derivative. I'm going to get rid of the constant, and I'm going to get rid of the pole. So now, I'm leaving the derivative because the the differentiator appears here as well. And now the pole is at, well, 200 reds per second. So this is a 1 over 200. Which is 1 over 100 divided by times 1/2. And so this gives me negative 40 dBs, and this gives me negative 6 dBs. And so I'll have a minus 46 dB offset. So if this was minus 40, and we're saying that every big box is 10, now our offset is down here. And then the pole occurs at 200, which is this tick mark here. And so we get here from here to here, I need a straight line. Okay, so these three are the components of the closed loop sensitivity. So let's do that in orange. Again, we're offsetting the differentiator by what was 6 dBs down from what we had before. And we keep climbing, climbing, climbing. I think I have introduced a different slope here, because I think what will have to happen is we get this behavior. So in orange, we have the sensitivity of T with respect to P in decibels. And these are, of course, the straight line approximations of these quantities. And so to answer the question, which is less sensitive to uncertainty in the pole location, if we're operating at low-ish frequencies, then the answer is clearly the closed loop system, right? So at omegas less than P, the answer is the closed loop system. At omegas larger than P times 1 plus K, right? So if we're now looking at this band, then the two are comparable. Then it's a toss-up. Okay, but primarily I want you to see that the open loop system is never less sensitive to P, right? Because this orange curve is going to be approaching the red curve from below. The closed loop system will always have a slight edge over the open loop system. And again, we are designing systems to make them less sensitive to parameter variation. All right, thanks for listening, and I will see you next time.